Hello, my name's Ed Robinson. I'm an SRE here at Cookpad, and my job basically is part of a team that keeps the lights on for one of the world's largest cooking social networks. I didn't get the memo, so I've got no cooking tips for you. We're going to talk about design patterns instead. So I don't know, like pasty folding or something. That's all I can manage. So design patterns in software engineering is all about kind of having like this library of vocabulary that we can use. Reusable kind of shapes and kind of having this reusable vocabulary that we can use, and we can look at a particular problem and say that's a decorator, you know, that's an adapter. This kind of thing lets us kind of, when we're a software engineer, have best practices that we apply to this situation comes up, I'm going to pick this thing off the shelf, and it makes us more effective. It means that we can communicate better with our colleagues when we're working on a problem. But patterns are not implementations. Patterns are kind of like this fuzzy, theoretical, kind of the general thrust to a problem, I feel. And patterns kind of really emerged out of object-oriented programming. And maybe you like object-oriented programming, maybe you don't. But I think design patterns and this idea of having like a structured way of thinking about how we design software is really interesting and really important because it gives us shared knowledge, and it's kind of the foundation for us to build good abstractions. You know that when we abstract things from the lower level to the higher level, it means that we write less code and we can be more effective as software engineers. But in order to get the right abstractions, ones that don't cost us more than they give us, we have to kind of have this shared knowledge and this shared way of thinking about things. We have to be on the same page with our colleagues when we're working in the kind of environment when we're all writing code for money. We're working with other people. I think that's pretty much that. I don't know, there might be one or two people who are a software engineer who works in a team of one, but very soon, if you're writing code for money, you're going to be on a team with some other people, and then you need to be able to discuss code in like kind of a shared way. You need to have these shortcuts. That's what design patterns do for us in software engineering. Design patterns, kind of as a concept, started to arrive in 1993. This book, Code Complete, you can see up here, was published by Microsoft. It's a really big book. It's really rigorous. Like, really don't read it. But the year after that, 1994, this book came along. It's got a really long name, but everyone just calls it The Gang of Four. This is kind of a really good book to read, and I'd kind of recommend you do read it, but yeah, it's a good book, but it's quite dogmatic about kind of what they think about design patterns and this kind of thing. And I think I kind of take a much looser view of what design patterns are and why they're valuable than they do in The Gang of Four. And I really like the Martin Fowler book, the book that came out in 2002. I think this sees kind of design patterns as kind of like a mature concept, and has really kind of where they've come to in software engineering. I think since 1993, design patterns have become something that if you're a software engineer, you should know at least a little bit about design patterns. You get to talk about these different patterns, especially if you're doing object-oriented programming. It's super useful to have that vocabulary at the very least. And, you know, to have this kind of understanding, and especially if you're learning how to do software good, just implementing these design patterns a ton of times, you work out how to do software good. I think it's kind of like, if you think back to maybe the past before there was software and people were working in factories bashing on bits of metal to make stuff, You spent 5-6 years bashing on bits of metal to make stuff. Design patterns are kind of like the apprenticeship thing, where you're just bashing stuff with a hammer day after day, and you don't think you're getting anywhere, but I think you are. So I was pretty interested a couple of years ago. This paper called Design Patterns for Container-Based Distributed Systems came out. It was submitted to the Usenix conference. It's called something like Hot Topics in Cloud Computing, something ridiculous like that. But it was written by Brendan Burns and David Oppenheimer. And Brendan Burns was one of the founding engineers from Kubernetes. So I think I care about what this paper says. And if we think about containers, Google has had this thing called Borg and has had these things that look a little bit like containers for over 10 years. So anyone who's doing stuff with Docker, which has been around, I don't know, 5 years at most, should really listen to what people who've had experience messing around with this stuff and at Google scale have to say about it. A bunch of people talk about this GIFy thing, Google's infrastructure for the rest of us. And I think it's the idea that Google are running these massive systems, Facebook are running these massive systems, Twitter are running these massive systems. And I think as people who care about infrastructure and delivering code at some kind of scale, probably none of us at Google scale, but if you're running 10 servers or 100 servers or 1,000 servers, like suddenly this stuff becomes really interesting because it's a force multiplier. As a software engineer, I don't want to be the guy who's like doing sysadmin stuff and trying to deal with all of these servers and stuff. I care about software and I care about doing useful stuff, not doing busy work. So the patterns and the kind of processes that have come out of places like Google where they have, 1,000, 2,000 engineers per server, the other way around. They have thousands of servers per engineer. Means that these practices clearly work as a force multiplier. It lets you be effective as an engineer and manage software running at a massive scale. So I guess it's a mental exercise, reading the paper, thinking about what it says. That's pretty interesting. So I'm going to talk about 3 kind of areas that come out of the paper, and then something new that I think is missing from the paper, mainly because it was written like 2 years ago, and we thought of new stuff since then. So there are patterns that involve single containers, patterns that involve multiple containers running on a single physical machine. This is what we call pods in Kubernetes. I think this is why Kubernetes has pods, and other container orchestration systems didn't have a concept of like a group of containers running together, because people in Google had seen these patterns in the way they wanted to deploy software and found them really useful. And then we're going to take a look at some patterns that work on multiple nodes, and then something new that they forgot about. Well, they didn't forget about, it wasn't invented yet. So containers provide a boundary, a bit like objects in object-oriented programming provide a boundary. When you've got an object, you get to interact with methods and maybe properties if you're not using Ruby, but you should just interact with methods. Containers are not really such a defined thing as an object. Containers are really just like a bunch of kernel features patched together to make this somewhat cohesive thing. So we can expose all sorts of things out of a container, but thinking about the boundary and what we choose to expose is super important. Clearly, a container that we make for a purpose has to expose some application-specific functionality. If it's a web server, you have to be able to expose a port running that web server so you can access it and do something with it. If it's a batch job, you need to be able to read some files from somewhere, do some stuff, write some files somewhere else. You've got to be able to have the kind of the hooks into your container for it to be able to do good stuff. And then there are management hooks. They're about to make sure our containers are doing the right stuff, behaving how we think they are, to debug them, stuff like that. So the first kind of design pattern we have for containers is we need some kind of interface like this. The names might not be exactly like this, but if we're going to be running application containers that contain a single process, we're going to need some kind of interface like this at minimum. We need to tell it to start and stop, maybe pause, maybe not, I don't know. But we need to have something like this to make it work. So that's our first boundary, the first set of management hooks we care about. We have some upwards interfaces. These are the interfaces that our container uses to tell us and our management platform, our control plane, what it's doing. So in Kubernetes, you can define some health endpoints, and you can tell Kubernetes to run a process or to make a network request to a particular port, and with some configuration to something to say, is this container still alive or is it stuck? Have I got my threads deadlocked? Is nothing working properly? So that's a really interesting thing. Your container can expose to your control plane how much resources it's using. We might use a tool like CAdvisor or Sysdig, or there's all sorts of tools that let us expose out of our container how much CPU is using right now, how much memory it's using right now, what it's doing to the disk, what the network looks like, all these kind of things. They're really interesting things that are management hooks we can expose out of our container. We can do application-specific stuff. Maybe you've got, statsd stuff being pushed out of your container. Maybe it's a Java application and it's doing a JMX thingy. Maybe you've got Prometheus endpoints exposed from your application. And then maybe you're writing something to standard error. Maybe you're writing out logs. Maybe you're, writing logs to a file somewhere, something like that. Maybe you're writing logs to some other interface. Then there's the downwards interface. This is the way that our application can pull in information, I guess, that it wants from the environment. So there's application-specific stuff. Maybe you've got environment variables to tell your application what its database password is. You've got environment variables to say, run in production mode, please, or run in debug mode, or something like that. You've got some formal lifecycle guarantees. You've got the contract between the platform that's running your container and it to understand what goes on when my application starts. So I have to do something special to make sure it's going to be running properly. And what happens when I want to stop my application? It's not reasonable to expect an application developer to know and design an application so it's able to handle being forcefully killed at any moment without, leaving stuff in a bad state. So we need to have some formal guarantees between ourselves managing the container somehow and the containers itself, the applications running inside. Service discovery is really important. I guess this is the biggest downwards interface. When you're running a traditional architecture with servers, where you can have a spreadsheet and go, yes, my hello world service is running on servers A, B, and C. My super important Cookpad social network is running on my servers that I've named after, my favourite characters from fictional novels. This kind of stuff. Service discovery is maybe not so important. Your service discoveries look through your spreadsheet and, edit all your config files or whatever. But when you've got a highly dynamic environment where containers are started and stopped and run in all different places, service discovery suddenly becomes super important. And Kubernetes especially has something called service accounts, which we'll have a look at in a second. Formal lifecycle hooks. When you run Docker stock in your Docker container, by default it does a sigtum and then waits some number of configurable seconds, and that's a contract between the environment and your container. It should, by rights, clean up what it's doing and, gracefully exit. If it doesn't, you can kill it later on, some number of configurable seconds later. That's a contract that you have between the person who's writing the application and the person operating the application running the container. That number of seconds, I guess. You can go a bit further. If you write in a Docker file, you can put a stop signal in. We use a tool called Rescue, work queue management tool, and it's written by some people, not us, and they've decided the way to gracefully make Rescue shut down and not leave jobs in a half-done state is you do a sig quit. So you can specify that in the Docker file, and then when you run your thing with Docker, it should gracefully shut down when you do Docker stop. And if you do this in the Docker file, then Kubernetes behaves properly as well. Kubernetes doesn't yet, I think, provide like a native way of deciding what signal you're going to have for the Docker stop. It just does whatever you've configured in Docker, but I think they might be adding it. Kubernetes gives you some other sort of lifecycle hooks if you want to do something more complicated than just choose which signal you send to your process. So they've got two hooks. You can hook in at post start and pre-stop. Post start kind of randomly starts any time after you've started to run the container, but it's not guaranteed to happen before it started, and it's not really guaranteed to happen after. So it's just generally at the same time the container's starting up in parallel. This post-stop hook gets run. There's a pre-stop one, and this one is guaranteed to have run and within a certain timeout have finished running before you blam in and hit your container with a hammer and cause it to die. So if you've got some more complicated way of cleaning up your container that doesn't just involve sending a signal to it, you need to put it in there. Lifecycle hooks like this, you can use some sort of execution inside your container. You can run a script, or you can hit some sort of HTTP endpoint as well. So depends on what your application is doing. If it's a batch job, maybe a script's more appropriate. If it's a web server, maybe you could just expose another endpoint to take that up. For service discovery, I think kind of the main ways you get that service discovery information pushed down into a container, the simplest way, I suppose, the easiest to implement is environment variables. And that's fine if you've got an application that's written to read environment variables, but I guess it's not. Some people's applications are written like that, some people aren't. So if you're writing a new application, that's fine. They're quite good. Environment variables can't really change after your process has started though, so in a highly dynamic environment it's not that useful. DNS is really ubiquitous. It's a bit crappy, but it's really ubiquitous, so pretty much any application that's talking to things on the network is going to know how to do DNS resolution to find out what it's talking to. There's pretty much no applications left that don't know how to deal with DNS, so if you're putting an application that you didn't write into a container and you want to do service discovery to discover some extra resource, DNS service discovery is probably your only option. And then there's API driven stuff. Maybe you would speak directly to a Kubernetes API to find out where some service you want to speak to is living. Maybe you've got some other service discovery API, you could use console or something like that. Sorry?
Sorry.
So yeah, there are a bunch of different tools that learn where other stuff is running, and you can speak to an API or something. But that's fine. Obviously, you can talk to an API somewhere and get some information. It's not too interesting. This one's pretty interesting. This is about like a really strong contract that Kubernetes has with applications running inside of the container. If you want an application running inside of the container to be able to speak to the Kubernetes API, it provides this really strong contract for you. First of all, there's a DNS name, Kubernetes, and pretty much if you've got DNS set up properly in your cluster, if your cluster is compliant and is a real Kubernetes cluster and everything's working fine, you can speak to the DNS name Kubernetes, and on the other end will be the Kubernetes API server. There are also these predefined places that are always the same. They give you a CA certificate for your SSL, gives you a token, and then also a file that has the namespace that you should use to sort of start off your API operations as well. So this is the kind of interface. Like there's nothing special about it. It's just a bunch of files in a certain place. But it's this kind of thing that you need to think about when you're thinking about the contract between your platform and your containers. You need to think about how do we have these really well-defined APIs that use kind of ubiquitous stuff, files and things, and just specific names, so you have this way for these things to speak to each other. And I think it's not mentioned in the paper, but I think ubiquitous interfaces are really important in making these kind of patterns of communication between containers and the outside world work really well, mostly because it lets you put applications that were not really written with running in a container in mind inside of a container, and you can get them to work sooner or later. Writing to a file system or reading from a file system is really ubiquitous. Reading and writing to a standard in and standard out is really ubiquitous, and DNS is as well. So the next bit they come on to in the paper, and this is perhaps the most interesting bit to me, is about what you can do when you're running more than one container together in some sort of arrangement. So there's the sidecar pattern, the ambassador pattern, and the adapter pattern. So the sidecar pattern is when you're riding on your motorbike and you don't look cool enough, so you give your dog sunglasses. No. The first and most important, most common pattern for multi-container deployments is the sidecar pattern. Sidecars extend and enhance the main container. So here's some examples. You've got a web application and is writing some logs out to some shared file. It's writing some logs to the file system. If you've got another container along and share them out, you can run your log management agent, Logstash, FluentD, Beats or something, some kind of hip-hop log management agent. Right, that's pretty interesting. You can do kind of the reverse as well. You could have a shared volume, and you could have some tool here. Let's say it's pulling the source of your static site off GitHub, and it's running some process to generate some files, and running Nginx in the other container over here. That does some really interesting things for you, because by splitting up these two processes and not running them inside the same container, running them in completely different containers, and the only thing you share here are the files that are written out by this process, you get kind of separation. So your web application, if that gets, your Nginx, if that gets vulnerable and someone gets a shell on that, you can't really do anything but read the files that your web server is serving. You've got maybe your GitHub credentials in here, so you can pull down your private source. Maybe it's talking to some APIs to pull the latest data in to make your wonderful, almost dynamic pages that are generated inside of a great big whirlwind in your container here. That's quite interesting, that you can have this kind of separation of containers. So in the paper, they talk about 5 kind of advantages to having an architecture where you split up the components of your application into different containers. Right? Both of those examples, there's absolutely no reason why, if you were using a modern programming language, you couldn't write an application that did both of those tasks in the same process, in the same container, without that separation. Why would you want to do that? So, number one thing they talk about is resource accounting, which is a weird sort of googly way to say that you can set different C group limits on the two containers. So the web server, you want to be able to use lots of CPU and serving requests as soon as it possibly can. The log management thingy, maybe you don't really care about that using crap tons of CPU. You can be okay with that just kind of sipping at your CPU and uploading your logs with a much sort of lower priority on the resources on the machine. You get this kind of packaging advantage because they're in two different containers, two different container images, maybe pushed to two different registry, and you only bring them together at the time when they're running on your system. They could be managed by two different teams. They could have clear boundaries and responsibilities between those two containers, and that can be really useful in a large organization. Maybe you have some engineers in your organization who are really knowledgeable about log management, and some who are really knowledgeable about building containers to run Nginx. And those two teams, as long as they have a clear contract between them, don't need to collaborate so much. They can be working in different time zones, and they can be happy that because they've decided on this clear boundary of responsibilities that they're able to make stuff work good. Number three is reuse. You could have hundreds of different web applications, but as long as you stick to this kind of common contract between your web application and its logging thingy, it's really fine to reuse that everywhere. So you can have two engineers working on your logging infrastructure, and they could support maybe thousands of engineers building all sorts of, different applications that all make use of that shared functionality. So that's really interesting. Failure containment is a fourth really big benefit for splitting stuff up. If you build this log management thing that maybe pushes all of your log files into Elasticsearch, what happens if your Elasticsearch cluster goes down? Does your awesome website go down with it? That sounds like a really bad situation. If it's running in a completely separate process, in a completely separate container, who cares? Your web application can go on serving, and maybe you'll lose some logs, but not so bad. And then there's some deployment advantages. Clearly, the people who maintain the log management tool aren't interested in deploying as often as the people shipping hot new features to the web application. So those people can have different schedules, and they can, push those containers into production at different times. The ambassador pattern is about, of course, the most delicious, is about providing a simplified view of the outside world to the container. If you imagine maybe you were an ambassador for the United States of America, making no comment at all, but imagine you were an ambassador for the United States of America, and the country you're posted to has a really complicated political situation. You might want to dumb things down a bit before you go and speak to the president. Here are some examples. Okay, you've got a web application. It depends on Elasticsearch because you're on AWS. They have this thing called the AWS Elasticsearch service, and the really, really cool thing about this is if you want to make requests to Elasticsearch's HTTP API, which clearly you do if you're using Elasticsearch, you have to sign every request with Amazon's weird HMAC authentication do-flipping. If you've developed your application on a developer's laptop and they've installed Elasticsearch, everything works fine, you try and deploy to production using AWS's awesome Elasticsearch service, it doesn't work. So there's this project on GitHub, it's really good. Lightweight little HTTP reverse proxy thing. You speak to that, it looks just like your Elasticsearch on your computer. You speak on localhost for 9200, and it talks to the AWS Elasticsearch service, does all of the request signing stuff. All of your requests are secure, everything works, awesome, and everything to do with your application works exactly the same way on a developer's machine as it does in production. That's pretty interesting. Same thing here. TWEM proxy is a thing that Twitter made. If you've got Memcache on your machine, you run one instance of it. But for scaling reasons, when you're running, what's that small website called? Twitter.com. You probably have got lots of Memcaches, and you want to shard all the keys that you're sending off to different ones so you can scale. So there's this proxy. It's really lightweight. Uses a few megabytes of RAM, teeny tiny little bit of CPU, but it shards all of your requests to put stuff and get stuff from Memcache, and so you can run it alongside your application here. Just speak the normal Memcache protocol to the proxy. It looks just like it would on your local machine. So that's really useful. There's other kind of tools just like this that you can shove into a container to give your application a simplified view of the outside world, so it's easier to develop. Your developers don't need to know or care about the intricacies of running stuff at scale or whatever else. There's proxy SQL you can run to do like pool management and stuff like that for MySQL. You could use HA proxies, a really general purpose tool you could use for both this kind of thing. Google have a thing that they use in YouTube to make MySQL really scalable, or something called Vitesse, and that works by shipping a special proxy that investigates every query and sends it off to the right database for you when you make it from the YouTube application. So there's loads of examples of this pattern, and it's really super useful. You get the adapter pattern. This is all about putting a square peg into a round hole. It's in fact the exact opposite of the ambassador pattern. Adapters provide the outside world with a simplified or changed view of our application. It lets you standardized output and interfaces across multiple containers. And at somewhere like Google, where they have like this kind of uni repo and everyone's forced to use the same libraries, maybe they don't really care about this stuff so much. But if you're in a normal company where everyone has seen like the hottest new technology and decided to use it like every day, like having this way to kind of sort things out is really useful. So let's say like, I don't know, 5 years ago you got StatsD and you started pushing metrics out of your applications over UDP, but Prometheus is the hot new thing. There's this thing called Prometheus StatsD exporter. You run it in your pod alongside your application, and you don't have to change anything about your application. It's still pushing out StatsD metrics, but they get turned into metrics that can be scraped by Prometheus, making HTTP call to 9102. To the outside world, to Prometheus, it looks like you built your application with Prometheus support built in, an endpoint that you can scrape the metrics of, but you didn't, you're just running an adapter. So that's the three kind of patterns for multiple containers on a single node. Then there's the multi-node patterns. Leader election. When you've got any class of problems that involve coordination and you want to run them across different computers, you're going to probably end up having to do some kind of leader election. Leader election is hard, but there are libraries. But they're hard to use, and actually they might not exist for your chosen language. I think Ruby's really cool, and I thought, leader election, that sounds like a thing that there should definitely be a gem for. There's one that I found, and it doesn't look very good. So, what might you want to do about leader election in a containerized environment? Sounds like you should have a sidecar where you use the best of breed leader election thingy, console or etc. etcd or something like this, and you build a thing that can be shared across your organization, and all of your applications that need to do leader election can speak to some really ubiquitous, easy to use interface. They'll probably make a call to an HTTP API that's like, oh, get, like, make me the leader, and that thing only returns 200 if you are in fact the leader, and all of the other times you can just sit there idling, keep calling your make me the leader endpoint. That kind of thing works really well and simplifies away from your application code doing hard stuff. You can hire 1 or 2 experts for your company who are really good at building leader election thingies, and then you're going to have hundreds of engineers who don't need to care about the details of how you do it properly. If you're using Kubernetes, Kubernetes provides some primitives that let you do leader election really well, because there's etcd running inside of the Kubernetes API. The Kubernetes Go client library, in fact, provides you like a client that you can just call some methods that do leader election for you. But you might want to put that in a sidecar and make that into this really simple little service if you're using some other language that's not Go. Next pattern, work queue. We're really good at queuing, we're British. So work queuing is something that's been around for ages. It's a really good pattern. I found like papers that talked about building work queues and stuff going back to at least the early 70s. There's probably stuff earlier than that. The previous generation of tools that we're working with right now often been coupled to a single language. There's tools like SQ and Sidekick in Ruby, Celery in Python. I don't know about other languages. There's probably loads of them. Or maybe you could use a tool that requires some assembly. Maybe you get RabbitMQ and you write into your application some code to do the work queue thingy, or you're using a service like Amazon SQS, do the same thing, write your own stuff, use their APIs or their client libraries and build your own work queuing system. It's kind of complicated and difficult to build this kind of thing. In the paper they say the availability of containers that implement run and mount interfaces make it fairly straightforward to implement a generic work queue framework that can take arbitrary processing code packaged as a container and arbitrary data and build a complete work queue system. Use a container as the unit of work, running a container is your unit of work, and then your application doesn't need to know anything about queuing or how to be a worker or anything like that. It makes your application immeasurably simpler. Here at Cookpad, we built a tool called Barbecue. It's a work queue implemented on AWS SQS. You run a management dashboard thingy and you run a worker. When your jobs get queued into Amazon SQS, they get run by launching Docker containers on an ECS cluster. The data is passed in with a ubiquitous interface. We pass in environment variables with the data in, rather than using a volume mount like they do in the paper, but same thing. So there's a web console here where you can manage your jobs and you get metrics and stuff out. And this is really good because when people in Cookpad write something that needs a work queue, they don't need to implement this in their application. They're just writing batch jobs that read some data from the environment variable, do some stuff, and that's it.
Hey, sorry, can I ask a question? Because a lot of queuing, the reason why a lot of the time you write application queues, or where you use tools like RabbitMQ or ZeroMQ or something like that, is because actually you want to do some business logic about the prioritization of jobs or tasks within that queue. It strikes me, I can't see how you would do that with this.
Yeah, sometimes you do. But yeah, this is using Amazon SQS underneath, so you have all the semantics that you get from having different queues for different tasks and stuff. We have like a really thin client library. There's a really simple HTTP API. You can queue a job onto it, so you can queue it onto a job with a name. It gets run by the workers with the name, and the worker is not like something that's running all the time. It's just a bit of configuration that we configure in the dashboard, and that goes ahead and launches the right container for us. So I think you get all the features you do with like highly intertwined, highly coupled thing, but a whole class of problems go away by not having all of this code for doing queue management stuff that is really orthogonal to the purpose of the application. You want to take a thing and run some code, right?
Yeah.
And by having everything in containers, a whole nother class of problems go away. If you've got a memory leak, it only matters for the length of time that one job takes to run. Your container launches, runs, cleaned up, gone away.
Yeah.
It's taken a while, this. I thought it would be a bit quicker. Something new. So this isn't mentioned in the paper, but it's super interesting, the operator pattern. This is something that CoreOS came up with about 2 years ago. It's kind of Kubernetes specific, but I think it's another pattern that's really important for dealing with containers. So Kubernetes and systems like it are configured declaratively. I'm not going to put the JSON up here, but you ask for Kubernetes to run 4 pods for you. The pods are run, and they keep on running, even in the face of failure. If one of your nodes goes down, if there's a bug in your application and it exits early or is killed because it's got a memory leak, Kubernetes will sort out a new one coming up. Internally in Kubernetes, there's something called a controller. And a controller is a kind of concept that's well known. A control loop is something that's well known from lots of kind of industrial control applications in the real world. The simplest example is really a thermostat. When it gets too hot, your boiler switches off. When it gets too cold, it switches back on. That's implemented with 2 bits of metal glued together and they hit some contacts. We can do the same thing with code. We run this big loop. We observe the state of the system. We analyze what's going on. We work out what it will take to fix the diff of our desired state between our observed state, and then we do something. We act on the error to correct it. That lets us build systems that converge towards our desired state all the time, even if loads of really weird stuff happens. Even if we've got bugs in our application that mean that after 30 minutes they die, even if we've got slow memory leaks that means we have to kill them off every 30 minutes, all of that stuff is fixed for us. We don't care. Well, maybe we care, but it's not the issue that brings our site down, it's an annoyance. So the operator pattern is that, but it's a little bit more. It's about thinking about what are the realities of operating a piece of software in real life. If you're running a stateless web application, just a simple control loop is fine, okay? But when you're running like a clustered database, Kafka, something complicated where state is involved, there's probably, you've got runbooks or scripts or something to do different procedures. When you scale up Kafka, you want to rebalance your, what do they call queues, partitions. When you downscale Elasticsearch, there's some procedures you want to follow to avoid some data loss to make sure that you've got enough replicas and everything's going to be okay if you kill off one of your machines and the data can migrate over onto the remaining ones. If everything's completely destroyed and all of your machines have stopped working, you need to download the backup from S3, restore it, start everything up again. And taking backups, that's another thing that you have to do when you're operating software in real life. That doesn't neatly fall into, I can just do it with Kubernetes. I can just set up a deployment and that runs enough pods for me all the time. This stuff is more complicated than that. So we need, first of all, a way to configure this in a declarative way. Kubernetes gives us a thing called custom resource definitions. This allows us to add new types to the Kubernetes API at runtime. And they let you do a lot of the stuff you can do with every other resource in Kubernetes. You can create, update, delete them. They've added in the most recent Kubernetes that you can, with just kubectl, scale them up and down as well. So you can perform all the sort of common actions on them. So the operator pattern was introduced by CoreOS in 2016. It's basically a custom controller that has all of your operational logic baked into it and a custom resource definition. So it turns all of your operational logic about how you manage your particular database, or Kafka or Prometheus or Rook or Elasticsearch or whatever, into these declarative things. You say, create a database, please do a backup once a night at 15 minutes past midnight. If my database goes down and is completely destroyed, restore it from a backup. That's what an operator lets you get. You can build your own as well. There's a whole bunch of them out there. There's like literally lots of them now. There seems to be mostly operators for running OpenStack on top of Kubernetes, which sounds crazy, but there's a lot for that. But you can build your own. If you want to use Go, there's a project called Operator Kit that seems to make it really simple to write your own operator. If you can make the logic for maintaining your application fit into some Go code, you can shim it into this Operator Kit kind of framework thing, and you should be able to build it. You can use the standard Kubernetes client library. And there are client libraries for loads of languages that are progressing really fast for Kubernetes now. I don't think they're really ready to build one of these things yet, but they will be soon. So my talk is almost over, hurrah. It took ages, but a few thoughts to end. Boundaries really matter. Boundaries organizationally between your operations team and your developers, between your developers and your product managers. It's really important to have contracts, documentation, clear responsibilities, socially, in work, in software, in systems. Really, really important. Think really hard about interfaces. As DevOps operational people, what is the best interface for us and the work we do? Is it please open a ticket? Or is it something better? Can we provide better software that gives the people we're working with better interfaces to the stuff we're doing? And it's over. I'm on Twitter. I talk about stuff. I'm in the middle of writing a book about Kubernetes. Follow me on Twitter, I'll let you know when it's done. It's going to be awesome. Write some blogs and do some videos and stuff. And Cookpad are hiring SREs, so come and work with me. And I'm really bad to work with. Such an idiot. Stupid stuff all the time.
That's great.